Okay, well, let's move on to the second topic of this first presentation, which is slope stabilization. And a lot of different things involved in slope stabilization, so this is the one session that will go a little bit longer here. Basically, I look at slopes and instability problems three ways. One, first, you want to avoid it. If you can stay away from an unstable site, you can save yourself a lot of headaches and often a lot of money. Second, you want to design to try and prevent failures with the proper, appropriate slope angles for the type of soil you're running into. And then when still things fail, and it'll happen, it happens even despite the best of engineering design and good observations, slides happen. And so then you get into a pretty wide range of stabilization alternatives. How do you deal with it? And here's just shallow little slumps that aren't too problematic. This lower one down here, which a lot of times I try and move the arrow and it won't move. I don't understand why. The little green arrow there. Maybe if I refresh it here. Nope, still can't move it. Right on the next slide. Anyway, I'm sorry. So this lower photo here is often a little cut bank failures mess up road drainage as well as being something you have to maintain and clean off the road. Another type of common problem is these just shallow failures. Who's moving the arrow? Is that me or? Anyway, these on fairly steep cut banks, like one-to-one cut banks, if they're covered with just grasses with shallow roots, often you get just these shallow failures, like in the upper two photos. The lower photos are fill failures, typically because of side casting and not getting compaction on a fill on a steep slope. And then you get to the bigger failures. These are the ones that ruin your day or make your day if you're a design engineer, because they're going to take some serious repairs to try and fix them. This upper left one's a fill failure. The upper two are fill failures. The bottom two are where just part of the road's missing. The bottom right one, the bottom of the road's just buried. And so once you're looking at something like this, you're probably dealing with this on a permanent road system, but you're looking at might be some fairly moderate repair costs once you come to this type of a situation. First, talking about avoidance, you have to know what you're looking for. This is just a scarp from if you've got a crack in the ground like this, it means some of the ground is moved. This Jonathan, my colleague here, he's probably smiling because we're hoping that we're going to get some federal highway or some storm damage funds to repair it, because a lot of these things are pretty expensive, and we often don't have the funds to do it in our own budgets. The sort of things you really look for, the most common signs of instability out in the forest or areas, the hummocky terrain, the bulging, the groundwater, the seepage areas, and trees that are all jackstrawed that are pointing in different directions. There, finally. So you got trees that are just leaning like this rather than straight. And this hummocky terrain comes at benches and forms kind of terraces, kind of product of years of movement. Or sometimes the road's just gone or buried, then it's pretty obvious. So those are things you want to avoid. Then kind of in the prevention department, we try and design to slopes that we think will be stable. And for instance, in here, this was a fairly well cemented soil, so it stands almost vertically. Or bedrock will stand vertically. That's fine. But once you get into a looser soil, a sandy soil, or something like this is on about a 1-to-1 slope, one horizontal to one vertical. And so it really depends on the type of soil you're dealing with. But and field observations help a lot to decide what may or may not be stable. Looking at this on this drawing here for cut slopes, probably the standard range of cut slopes, if it's in rock, we may specify a 1/4 to 1. That's a 1/4 horizontal to 1 vertical. And so it's almost vertical. If we're in most soils, you're probably over in this 3/4 to 1 or 1-to-1 slope. It's considerably laid back, and that's what will be stable for the long term. And the other thing we want to do if on construction, anytime we have a choice in slopes that aren't over, say, 50, 60, 65%, is try and balance our cut and fills just because that reduces the cost of construction. You don't have in-hauling. You don't have movement of materials. So you're taking material from your cut here and putting it directly into the fill. When you get over, say, 60%, you're looking at just a cut. You probably don't want to be filling, and so that means you're having to in-haul the material someplace, and it adds considerably to the cost of construction. But it's a reality in steep terrain, which is why we try and avoid steep terrain if possible, and understand that steep terrain is going to be expensive when we have to work in it. Fill slopes, the other side of the road, again, probably the most common fill slope angle you run into is, say, a 2-to-1 slope. And the advantage of a 2-to-1 is that it can help promote revegetation. This is just based on the strength of most soils. Soils will stand typically at a 1.5-to-1, but it's a little harder to get vegetation going. If you're on fairly steep slopes, it often pays to put in a terrace. It's kind of like a foundation underneath your fill. It's a common practice on large construction on moderate slopes. Then, like I say, if you get over 60, 65%, you probably shouldn't be thinking about a fill. You probably should be taking your material to some other site. This list here from our low volume roads engineering guide is common slopes. I don't say recommended because it's so particular to specific soils and where the conditions you're working in. But these are what I've seen, and it seems to work in most areas. Is in rock, it can be almost vertical, very steep. Most soils tend to be okay down in this 1-to-1 range, maybe a little steeper. Very loose granular soils, like just sandy soils, take that kind of like a fill slope angle of 1.5-to-1. And if you get into more clay soils, you commonly want to be laying them back even more like a 2-to-1, 3-to-1 slopes. That's cuts. Then in the fill department, like I say, we're typically down in 1.5-to-1 or 2-to-1 slopes. In other words, it's 2 horizontal for 1 vertical, less than a 45-degree slope. So those are just guidelines and field observations, probably one of the best ways to decide if those seem appropriate. I do want to mention this one aspect of vertical cuts. This is a picture over in some decomposed granitics, of which we have a great deal of in the Sierra Nevada. This is actually over towards Weaverville. But it's the thing about decomposed granitics and some cemented volcanic ashes, they will stand vertically or near vertically. They're often raveling, so you've got a lot of material like this, but you want to make them as steep as possible, both to minimize the cost of construction and the fact that if you lay them back flat, they're highly subject to erosion. And so you don't want to have any more surface area exposed as necessary because the raindrop impact will cause that erosion, so you keep them as steep as possible. But that's a decision you have to make, whether you want to keep it as steep, which has some risk of, in some soils, of failure, versus laying it back at a flatter angle, which is stable, more stable from a mass stability standpoint, but more erosive, more area exposed to erosion. Some things are obvious, if you're in pretty rocky material like this here, pretty well cemented ashes like you have a great deal of in some areas, Central America at least wise, it'll stand just about vertically, and you want to make your cut as steep as stable. So let's look at a lot of stabilization alternatives that we have out here. This happens to be a rock buttress from a highway project over towards Forest Hill area. There's a couple of things we want to look at first. If we want to, when we have an instability problem, we have to think about what are the real risks involved. And risk involves 2 things. One is how likely is it to fail, and 2, so what? If it fails, what is the consequences, or what are the values at risk? And those values are sometimes erode, sometimes water quality. So they're both both infrastructure and environmental values. The other thing is then, okay, if it's likely to fail, we have a pretty wide range of management options as well as engineering options. We may choose to do nothing. We may choose to move the road, just ramp up over a little slide area. And you have a lot of flexibility with low volume roads that you don't have with high standard roads that have much more stringent grade and alignment requirements. We may move the road. We may put in some sort of protection measures or netting or something to prevent failure, or get into this wide range of stabilization measures, which is what we'll be talking about next year. Okay, the key thing I think on stabilization measures, and this is a whole science or whole profession unto itself. We geotechnical engineers, we love it because it's some of my favorite types of projects. But you have to decide what's adequate and what's cost effective. So you're looking for the cheapest type of fix that'll stabilize the hillside. And so I kind of have these listed as what I think is as a way you ought to think about it, and how it affects costs. First, often we'll probably the most common thing we do is just remove the slide, and just live with it. Second, vegetation and drainage. That's the cheapest things you can do, and on a small, shallow slides, often may be adequate. We can lay the slopes back, modify them. There's a lot of types of small structures we can use. We can use reinforced fills on down here. We can get into, design larger retaining structures. And then there's the kind of exotic retaining structures, some of the deep piles, anchors, soil nails, which, I'll show you examples of all of these. And the price generally is cheaper from the top and gets more expensive to the bottom, although launch soil nails can be pretty inexpensive, and I'll mention that a little later. Okay, here's probably the most common thing we do is just dig it out. Just remove the slide material. Here we actually had the luxury of being able to shift the road out a little bit away and get away from the cut bank, as well as just removing the material. If we can get a particularly low cut slopes, if we can get them well vegetated, and obviously it depends on the climate. In the coast ranges, this would be a lot easier than it is in the Sierras and in wet areas versus dry areas. But if you can get a good cover of vegetation on it, you've probably solved a lot of your problems and reduced the potential for instability. Here's some examples. Just even conventional erosion control, particularly with good grasses and maybe mixed with some deeper rooted, some type of brush, may need more than enough to prevent a failure or to fix a small site. These other treatments up on top, this is a vetiver grass which has a very deep root. It's not native, obviously, to the U.S., but people like the World Bank use it a great deal in various countries. But the point is, it's got deep roots, and it's pretty. It's non-invasive, but it's not native, but it's also not invasive. And then this is some grasses that were planted into a cut bank, which was raveling. The big advantage of, these are from a variety of different areas, the advantage of roots or vegetation is just these roots. They help anchor the soil. This is a willow, a salix family, what we use a lot here in the West for some of our stream stabilization projects and also some slope stabilization projects. This is an example of conifers that are, it's basically buttressing the slope. These roots are anchoring the soil here, whereas next to it over here, the slope has failed. And this photo Don Gray sent me, and his book on biotechnical slope stabilization is an excellent old reference on this whole subject. And this one up here on top just shows, again, the effective roots that are kind of holding this dry slope in place. And next to it, it's raveling. Right here, it's holding because of the roots of vegetation. So vegetation's good stuff. And inexpensive, aesthetic, environmentally friendly typically, so it's a good place to begin. The treatments where you may be putting in layers of brush or some sort of live stakes, things like this. This was a brush layering treatment. Robin Sotier sent me this photo a while back of just layers of brush that then have grown up for a couple years and just get really nice dense mat of vegetation. Here are some gabion structures that are mixed with live stakes that John McCullough sent me. And then we get the true biotechnical um, sort of the structures. It's interesting. I look at these because some of these seems like little figures missing. But anyway, this is a live crib walls. This is in the North Coast. This is down the Bay Area with eucalyptus, I believe. But anyway, it's combining a physical structure with vegetation, so you're getting the best of both worlds. You're getting the physical structure, and you're getting the long-term root support from vegetation. So that's why biotechnical treatments are so nice, and they're aesthetic, very appropriate for certainly shallow to moderate failures. And I'll come back to drainage here. We mentioned this, started off with this, but if you can remove the groundwater or lower the groundwater table, then you can solve a lot of your instability problems. This is appears the fairly shallow trench drain for just a local instability. Here's was over on the Klamath Forest for a pretty deep landslide. We're using gabions for the drainage material, but it's got a perforated pipe. So this is just a deep underdrain, about 30 feet deep for a large slide complex. And then the other pretty common problem, if you have failures in a fill slope, or if you've got problems with your fill, you've got water coming in and failing, you're saturating your fill and causing it to fail, you put an underdrain or a filter blanket underneath the fill, something like this. Easier to do ahead of time than after you've built a fill, because if it fails, then you just have to rebuild the fill. But that means you have to recognize that there's that seepage there before you put the fill on top of it. Horizontal drains, they're mostly used in deep-seated landslides. We've used them quite a bit. If you can lower that water table on a large landslide, you can maybe spend $50,000 on horizontal drains compared to spending $250,000 on a retaining structure. So it's really lowering the water table. So you've got to hopefully see some results and be getting some water out of the system. You don't necessarily have to get a lot of water out, but at least you have to lower that water table for horizontal drainage to be effective. And I want to throw this in. I borrowed this slide from Don from last week. Thank you, Don. Surface drainage. You don't want to concentrate water on top of a slope or a slide. So if you can get the water dispersed over here onto a convex slope rather than onto a concave slope where it concentrates, you're much more likely to minimize a failure problem. Okay, rock falls, they're a particular type of problem, and I've done an investigation of some people that were killed in rock falls. A friend of mine was killed in a rock fall accident like this, and so it's something that we want to think about even on low volume roads. It just depends on whether there's much of a frequency and potential for falling rock, but you should address it. And a lot of different treatments. They're relatively expensive, so you can't afford to do it every place. But if you have a history of rock fall in an area, that's the place you're going to treat it. You may want to scale. You may want to remove the rock. You may want to build in some terraces, something to catch the rock. You may want to lay the slope back. You may want to use some sort of netting, in combination of netting and rock bolts, but ways to anchor the slope and pin it down to stop the rocks from falling. And here's just a couple examples. Netting along the road to stop the rock before it bounces out on the highway. Going back, this photo is obviously much more rigorous to stop this rock from falling in the first place, or to trap it before it gets to the highway. Or just moving the road out, putting a catchment along the road so that the rock it'll end up here rather than bouncing out onto the road. So there's a lot of things we can do, but like I say, you have to identify the problem typically before you're going to really deal with rock fall. Okay, one of the most common treatments if something's failing and it just appears to be over steep is to lay the slope back. You do it just with terraces. This is terraces in a cut slope, and these are often built into it, or if there's a slide repair built at that time. But a series of terraces here. We've got here on a fill slope a terrace here. And what these benches or terraces do is a couple things. One, it effectively flattens this whole angle, gives a place for the rock to catch, gives a place for vegetation to grow, and breaks up the long flow of water. So there's a lot of advantages to having terraces, and you usually see them maybe every 15 to 25 feet high on a high cut slope or a high fill slope. Fill slope stabilization, this failure here was a result of a spring under the road, so we should have had one of those filter blankets under it before we built the fill. And when you've got, there's probably two main reasons why you get fill slope failures. One is just over steep slopes. If you put on maybe a 60, 70, 80% slope, it's not going to stay there. And it's very difficult to compact unless you've built in some terraces. So it's over steep slopes like side cast, which is an old style of construction. And the second one down here is drainage. There was a big spring coming out from underneath the road here. So those are two things you want to watch for. And probably the most common way to prevent problems is with good compaction, both in layers for the fill itself and on the surface. And you can do that if you have maybe a 2-to-1 slope. It's not an over-steepened slope. Here you can see kind of what is ideally recommended for a fill slope. If it's very flat terrain, not a big fill, you probably don't have to worry about compaction. But if it is a very big fill, you want to get good subgrade strength, it's good to put it down in layers, maybe 6 to 12-inch layers, and compact it. And again, if you're on steeper slopes, you don't want to have a failure right along that organic layer or the contact of the fill and the old native soil. So you try and build in terraces. Costs more initially, but much better insurance against instability problems of fills. I want to mention disposal sites because they're basically just a fill. These are some examples. These are not in California. These are some examples of bad fill disposal because fill slopes, it's predictable. It's going to be about a 1.5 to 1 slope here. And here, if you know where you're starting here, 1.5 to 1, you know where it's going to end up here. And if this is choking off a stream, here it's ending up in a river. Those are just places you don't want to be putting fill. And this is a practice I'd seen way back when in the Coast Ranges over maybe Del Norte County, but I think those practices have been much improved now, fortunately. Here, what you do want to do is look for areas where knowing where the fill's going to toe out and end up someplace where it's not going to be doing damage in a fairly flat terrain, where it's an area like this away from water. And so that's why often we will designate disposal areas. Look for areas that are in flatter terrain, particularly if you're in mountainous terrain and doing earthwork. You want to know where that material is going to go so you can put it in a stable spot. And ultimately, probably put it in where you have, say, a 2-to-1 slope that you can get that slope revegetated. Reinforced fills, a certain a specific type of structure that we often use. And this is one, if you don't, here I'll show you, here's a couple of examples of using a geotextile, using a geogrid. And what these reinforced fills look like are layers of reinforcement. You've got these layers here of this reinforcing fabric, or it can even be welded wire mesh, but it's typically a geotextile or geosynthetic. And maybe 3 feet, 5 foot spacing depending on the height of the fill. And there's specific design procedures for this. And also little intermediate things or layers so that you can hold a slope like 1-to-1, where a natural soil won't hold it 1-to-1, but a reinforced fill will. Something else we also do is called a deep patch, which is rather than a full structural fix, we're only putting in, say, 3 or 4 layers of a geogrid or some geotextile, just to take something that's marginally unstable, like an old fill that's constantly settling because it was an old side cast fill, and building it into layers. Here's an example. This is not a very good example of safety. Where are their hard hats? But anyway, they're putting in several layers of geogrid to stabilize the road shoulder. So those are fills. Now the last area here is talking about retaining structures. Lots of types of structures. These are just some small little ones here. Rock walls, timber ones, not obviously not designed. Gabions are probably one of the most common type of structures that are designed. These are a couple examples of them in these photos. The key thing with gabions is keep in mind if it's a retaining structure, it needs to have a lot of mass to it. So you need to think about it like a pyramid. It's not just a facade. It's actually a pyramid mass of weight because you're resisting, a failure that's trying to push against it this way. So you've got to have enough mass there. A design I like is a thing called tear mesh, where it's actually is gabion facing plus a wire mesh, so it's actually a mechanically stabilized earth design, but with the comfort of having a gabion face, which a lot of people like. And probably the most common retaining wall we use today is the MSE walls or mechanically stabilized earth walls. Lots of different types of MSE walls. And this is one with just a geotextile face, timber face, modular block walls, welded wire. The big advantage of MSE walls is that you've got some sort of a facing element here, like these blocks. You've got reinforcement material, which is a geograde or geotextile, and you're commonly using local material or granular, a material that can be found someplace that's not too far away. So that's why on big structures, these are just cheaper than traditional gravity structures. These are a couple examples of ones this tire wall here I think still reigns as the ugliest wall I've ever designed, but it's still functioning well today. A common wall we've built are these geotextile walls where it's just a wrapped face, burrito walls that are sometimes endearingly known as. And this is just one of our design drawings of what that burrito wall looks like in the construction sequence. But you do have to protect the face. Here we've actually put some emulsion on it. In Japan they use a lot of these, and then they put a gunite or a concrete face on the face of it. But it's probably the least expensive wall you can build. Then there's a few exotics like tiebacks, H-piles. They're for certain locations where you have specific problems, deep foundations. Very expensive, very effective, but very expensive. And there's things like the soil nail launcher, which the Forest Service helped develop, and Soil Nail Launcher Inc., I think, with Bob Barrett, use it today. And you can come into a site, you don't have to excavate, so you can stabilize an area quite rapidly. So it has some advantages over conventional retaining structures. And just a couple notes here at the very end here. I just want to mention, because this was mentioned earlier, one of the earlier webinars on use of these geosynthetically reinforced bridge abutments. It's basically an MSE wall here with the superstructure placed right on top of it. And if you're interested in these, they can save quite a bit of money for bridges. You do have to be concerned about scour issues, so depending on the environment. And this publication here, which is a federal highway publication, it'll be on that list of references, is excellent, as it just came out last year. It's an excellent publication on design of these systems. And these are a couple publications, again, that are listed in your list here this is on cost-effective stabilization, TRB publication that just came out. This is a federal highway publication. The last thing I want to mention here is walls need good foundations. Most of the retaining walls I've ever seen have failed, and you don't want to see many of these things fail, but the ones I have failed typically because of a foundation problem down here. And this was one that gabions that just aren't set deep enough. Here we had a foundation problem. Here Ed Rose had a foundation problem here. So you've got to place them on something that's solid or deep enough that they're not going to fail. And that means sometimes you need drilling investigation. It adds to the cost, but walls can be expensive, so knowing your foundation conditions can be cheap insurance. So in summary on this whole topic, let me just go over these last points here. For instability problems, we try and use stable cut and slope angles, some of these common slopes that are adequate. But failures do happen, and if they happen, and we're thinking about fixes, you want to look at, get some sense of why it failed and how big it is. And then you look for the least effective, the least expensive, the most effective solution that you can come up with. And the first thing you try and look at is drainage and vegetation because it's the cheapest and most aesthetic solutions. From there, if that's inadequate, you move to structures. And if you're getting into big structures, you want to get into structural design. That's a whole other issue. We could spend days talking about that. But you do want to get into design or talk to consultants who do that type of design. And last, put them on a decent foundation because that's what will cause a slope to fail. And so that's it. Thank you for this first round here, and I'll leave you with that, and also just a photo of the prettiest wall I think I've designed, which is over on the Wasson Forest, whereas we tailored the rock color to fit the local bedrock in the area. Good morning or afternoon, depending on where you are. What I'm going to be talking about first thing this morning is on more subsurface drainage and then slope stabilization. And then the second hour we're going to spend talking about materials, roadway materials. On the drainage issues, last week, in the last couple of weeks, we've talked more about conventional culverts, fords, bridges. Don did a good job last week on surface drainage, and there's also the culverts. And so what I wanted to pick up is the other aspect of drainage, which is wet area crossings. And these are areas where there's perennially water coming out of a spring, coming out of a slope. And we basically have two choices of how we can deal with it. If it's a meadow area, we typically don't want to drain it. We want to actually maintain the flow, and so we're trying to just bridge over the water. And if it then in a more conventional drainage area or drainage method, if it's a wet area that's saturating a road subgrade, we probably want to remove the water. So we'll look at each one of those ways to deal with water. The first thing to think about as far as water is where it's coming from. If you've got a road that looks like this, if it's ponded on the water, if it's outsloped and you can get rid of the water and it dries up, no problem, or the ditch takes away. But if it's always wet, then it's probably coming out of a cut bank. It's coming out of a spring, and then we have to really be thinking about this aspect of subsurface drainage, crossing wet areas or meadows. And I might mention that this is not a good place for a road. It's probably a terrible place for a road, both because it's hard on the environment of the meadow, and it's hard to construct and fix and keep a road in good shape, keeping it dry. And so traditionally we've crossed these areas putting in, say, a culvert, trying to concentrate the flow and get it into one spot. But what we do is often create gullies through a meadow. We create head cuts, and we may dry up the meadow, so we're doing quite a bit of harm to something that's a fairly fragile and important part of the environment. So today, the approach, if we're crossing an area like this, where we, like I say, where we really shouldn't be, is ideally to put in enough drainage to keep the water table high, to keep the water where it naturally belongs. But what this takes is something like a permeable rock fill or a battery of culverts to keep the flow dispersed where it's always belonged. And so it's a fairly expensive treatment, but I look at it as making up for being in a bad place in the first place, a bad location. But sometimes we're there. And a great deal of this type of work's been done in the Southwest and here in Northern California, trying to fix roads that have been damaging meadows and drying up meadows over the years. The design tends to look something like this. On a lot of these figures, it's good to go to a full screen because you can see it much better, so you can see the detail of it. And here, where it just shows a battery of different photos, of different culverts. Where do I want to take the arrow here? Down here, we've got what would just be if you've got a moderate amount of water, you probably want to have put in culverts and make sure that the flow can be passing through the system and maintain a natural flow. If you don't have a lot of water, you may want to just go with just a permeable rock fill. Less expensive, but it doesn't have the flow capacity. So you really have to assess whether it's just perennially damp versus it actually has surface flow at times. The other thing you want to do is separate your rock. You want to keep it clean and permeable, so you typically separate it with a geotextile layer. Here you can see, now I don't know why it's only showing one of the two photos here, but it's a photo of a just typical crossing of one of these meadow areas where it's been put in with a drained, permeable rock fill and a bank of culverts. And like I said, it's a fairly expensive treatment, but it's making up for being in a spot where you probably really shouldn't be in the first place. So it's a relatively expensive environmental measure. This is kind of a time-honored approach, is to just put in something what we call corduroy logs or simple logs. You can bridge over a wet area. There's one picture of one crossing. Here's a little drier site, but same concept. The culvert pipes or the logs are put in parallel or perpendicular to the road, usually with water flowing across the slope this way. And it's time-honored. The only thing is it's really appropriate for temporary roads, not for permanent road systems. Let me move this arrow up here. And you can kind of see from this little drawing here, this cartoon, what that's supposed to look like. A corduroy road, it's only going to last maybe 5 or 10 years. Depends on the wood you use, but it does offer a way to cross wet areas, and like I say, particularly for a temporary road. Now, for a more permanent road, you get into what are some of the traditional underdrain approaches. And these traditional underdrains, they're more expensive. But the point here is you're not as concerned about maintaining the water there. The point is you're trying to get rid of the water. So in a temporary road, you might either use that corduroy or one of the best solutions just to not use the road while it's saturated. If you can wait till a dry part of the summer and use it, that's fine. But if you want to dry up the roadbed, then these underdrains are how we typically do it. You can see here there's water. Oops. Down. Water sitting here in the saturating the road subgrade, and if it's wet, it's just hard to have a good firm subgrade when it's saturated. Here you can see a typical underdrain, some of the details that go into it. Arrow here. You've got the permeable fill. You've got a perforated pipe, which is typically 4 to 6 inches. Your underdrain, to be most effective, is say 4 to 5 feet deep, and it's wrapped in a geotextile, something that is a filter that keeps this drain rock free. And a filter does two things. It lets water through it, but it keeps the soil from moving so that your drain rock in the middle here stays permeable. So this might be a typical underdrain. The one other detail is as Don mentioned last week, you want to put a cap on it because you don't want to be mixing that surface water with groundwater. Surface water is usually a much greater volume, so it would exceed the capacity of an underdrain. Here's a picture of what one looks like. This is from it's still doing construction. It hasn't had the cap put on it yet, but it's got the drain rock here. Problem is water's coming out of the cut bank here, saturating your subgrade of your road over here. So you've got this trench and underdrain to remove the water before it gets into the road subgrade. Here's a couple forest highway pictures of installations of underdrains. Again, you've got your perforated pipe, perforated pipe, your drain rock, and your geotextile filter layer around it. What's happening over here is if trenches get very deep, then there's a safety problem. OSHA doesn't like trenches over 3 or 4 feet deep before you shore them up or support them, so this is actually just a shoring mechanism to keep it safe in the trench. But like I say, these are a moderate investment, so you typically are doing this on a permanent road system. Now there are a couple other types of underdrains that are used today. One's called a geocomposite drain. That's it here. What it is just a plastic core wrapped with a geotextile filter and a perforated pipe down here at the bottom, down here. And so water's coming out of your cut bank here, goes into here before it gets into the subgrade over here. The other traditional type of underdrain that's been used for probably decades or centuries is a French drain. That's this little thing we have over here. And the difference of what a French drain is, it's just rock. It does not have it doesn't have this, perforated pipe here. And so the good news is it's less expensive, but the bad news is they're difficult to construct and really have something that works, because you've got to have like a graded filter here. They traditionally weren't made with a geotextile, and so you just had to go from soil to fine gravel or sand to coarse rock in the middle. So you don't have as much permeability or much capacity, and they plug more easily if you don't use a geotextile. So today, pretty much folks come back and use either geocomposite drains or the underdrain that I showed in the first place there. Here's a couple examples of some installations of geocomposite drains. One here, one down here. And like I say, they're quick to install. Contractors like them. They go in easily. You backfill them with the native soil on site rather than gravel. And I personally, I think, like the gravel drains more because I have a little more confidence in the design, but these are pretty effective, and so they're used quite commonly today, both in this application and as edge drains along paved roads. Now, what happens when the water is coming like up out of a spring under a flat road? Here, you go to this concept called a filter blanket rather than the underdrain. And so it's the same thing horizontally versus vertically. You've got filter cloth underneath it. You've got this permeable drain rock in the middle. You've got a filter cloth on top of it to keep it separated from, base rock over here, or whatever your surfacing material is. And that tends to look like this. Showed this drawing last week also. You've got your filter cloth here. You've got your some array of permeable perforated pipe. And one thing worth mentioning is that when you've got perforated pipe when you're in the drain itself, but once you get beyond the drain, or if you're going under the road or out across the shoulder of a road, you really want to go back to a non-perforated pipe because you don't want to be saturating everything around it. The point is to pick up the water, get it into perforated pipe, and then get it out of the system. Okay, the one other type of drainage that we run into at times are horizontal drains, and I'm not going to spend much time on that right now because I'll just be mentioning it a little later on when we come back and talk about slope stabilization issues. The thing about horizontal drains is they're typically used for stabilizing fairly large landslides. And I put these next couple in just because drainage is so important. We've heard about it now for a number of different sessions. There hasn't been one of these webinars that hasn't discussed drainage, and that's why the old joke that the three most important aspects of engineering design are drainage, drainage, and drainage. But another key thing is attention to detail, and particularly with drainage details. You've got a lot of little boorish but important details as far as where the water is coming from, whether you're going to get rid of it with the insloping, outsloping, whether you're going to have a ditch system and how you armor the ditch system, how you armor the outlets, whether you need under drains, whether you need filter blankets. So there's a lot goes into drainage, and the best time to see a lot of this is when it's raining, when water's flowing, and so it just demands detail. So I just wanted to emphasize that, and that got to pay attention to the details, probably as much as any aspect of work on low-volume roads. A couple good references. This Cedergren book on top is a classic textbook. Cedergren was a Caltrans engineer and wrote a textbook on all aspects of drainage. David Orr here at Cornell has a nice little primer on roadway drainage, covering all aspects of drainage. And this managing roads for meadow ecosystem recovery talks about the types of permeable rock fills and culvert systems that I was just showing initially if we want to maintain the water in a wet area. And this is by William Zedick. Another point I wanted to make is this whole field of geosynthetics. It's a topic where there's a great deal of use of them today, and there's good textbooks by Corner on the subject. AASHTO, the American Society of State Highway Transportation Officials, has specifications for their use. The Department of Defense, or Joint Army Navy, have some good publications. And the uses basically in low-volume roads are either for filtration, for drainage, for separation, or for reinforcement. So and each one has certain requirements. In this one textbook over here, the good news is Geosynthetic Design and Construction Guidelines. The good news about that is it's available from Federal Highway Administration. This new version that I'm showing here, you have to pay for. There's an older version on their website, which is available and free and has essentially very similar information. It just hasn't been quite as updated. But like I say, it's readily available, and this is based on a week-long course on use of geosynthetics. So it's probably the basic, probably the best primer around as far as a lot of good useful information, all aspects of use of